All right, so the question today is, are you exceptional? And I think we all like to think that we're exceptional in some way or another. I suppose what I'm interested in here today at explaining is statistically, are you exceptional or are we exceptional in a certain field of endeavor? And I think it's something that's worth understanding if you're trying to get good at something, just how difficult it can be to be, truly exceptional at something. Not to dissuade anyone from doing great things, but yeah, it's just interesting statistically. So let's just jump into it. What we're going to do is we're going to think of an example of a roller coaster. So imagine you got all these people that want to go on this roller coaster, and when you go to a theme park, there's certain restrictions on the height, and so we're going to say that the minimum height restriction is that you have to be 155 centimeters tall in order to go on the ride. We've obviously here got our continuous random variable, which represents people's heights that are attending the theme park and want to go on this ride. And then obviously just to recall that we've got density along the y-axis. Along here we've got density, and so that's just saying sort of underneath the curve, what's the likelihood that we're going to get, people between 150 and 160 centimeters tall. So that area underneath there equals the likelihood that people are between those heights. And so what we've got at the moment is the distribution that we're going to call capital X. So it's the distribution of riders' heights. So this is, lots of people, they're more likely to find people between 160 and 170 centimeters tall. Anyway, what we're going to look at in this video is a sort of what's called taking a linear transformation. So we're going to define some new random variable y rather, that's just equal to x minus 140. And in this real world example, what that would represent is how people's height above the cutoff. So essentially we're just going to shift everything left by 140. So now on the x-axis we have x minus 140, and you notice that we've got 0 here because we've taken 140 off. And so this cutoff now is you have to be 15 centimeters above the cutoff in order to get on the ride. And so the question I'm sort of interested in this video is, has that changed any of the variance? Has that changed the spread of people's heights? And I think you might have noticed that the shape of this distribution actually didn't change, and that should make sense. Essentially what we've done is, by taking away 140, we've just shifted everything left and made 140 the base, sort of the base case, or the baseline height. And then obviously people under 155 centimeters are not allowed on the ride, and those above 155 centimeters are allowed on the ride, because that was the distribution. So the sort of takeaway is that doesn't change the variance. And just recall, if we get a little bit mathsy here, that the variance is basically the expected value of the deviations squared. And you need to go watch the previous video, I hope, to understand sort of what this is all about. But what we can do now is we can say, all right, well, what is the variance of a linear combination of this random variable x? In this case, we've taken away 140. Well, we can see that sort of shifting it all to the left didn't change anything. The variance, the spread of people's heights, obviously didn't change. So we should come to the conclusion that the variance is what's called invariant under a horizontal translation. And, in maths, I've been thinking about this recently, this sort of computational people who love this kind of stuff here, this sort of proofs, and then this sort of big concept people, do not stress about this proof here too much. Just understand that it's, application of different properties of algebra and statistics. The thing we're interested in is, how did the variance change when we shifted everything to the left by 140? Well, we can see that the variance changes as a squared multiplied by the variance. So remember, b is our linear transformation. That's sort of the shift. And so this doesn't appear in our final answer. So shifting everything left or right obviously doesn't change the spread of people's heights. And that should make sense. Again, it's invariant to horizontal shifts. And so the variance is not affected by horizontal shifts, but it is clearly affected by, if we had an A value here. The A value here hasn't changed. So this is obviously 1. And, this is where it stretches the powers of my ability to make it real life examples. But let's just imagine we were then to scale everyone's heights up. So let's take a case where we had a equals 2. And so we ended up with this. So the variance, the new linear combination, is now 2x minus 140. So basically, you've taken everyone's heights and you've multiplied them by 2 and taken away 140. Let's look at what happens to the distribution if we do that. We're going to get something that looks like this. And you can see now that 140 is obviously the base case again. But you notice, and I'm going to go back there a bit, that the curve actually got a bit flatter, which is interesting in itself. Because what that means is the spread has increased. And then the question is, well, how did it increase? Well, it increased by 4. And it's a little bit tricky to explain, but let's just think about 2 people. If we were to take 2 people on our original curve, all the way back here, you take someone at 160 centimeters and you take someone at 170 centimeters. If there is that factor of multiplying by 2, 160 becomes 160 becomes 320 and 170 becomes 340. So people that were separated by a distance of 10 centimeters are now separated by a distance of 20 centimeters. So the variance has doubled in that case. And so when we come back to all of this stuff, the spread, if we change the curve here, has increased. It increases as the square of whatever the value is in front of x. So in this case, the variance increases by 4. Okay, so let's look at what this has to do with sort of anything worthwhile. And this is what we've got here is what's called the standard normal distribution. So you might be wondering, when is any of this useful? But this is to sort of answer our question now, are you exceptional? And what we can do is we make a linear transformation to what's called the standard score, which is called a z-score. And that looks like this, where 0 is the mean, and then you've got a standard deviation to the left and to the right. Don't stress too much about it, but basically this is how you do that transformation, where mu is the mean, sigma is the standard deviation. Remember, the standard deviation squared is the variance, so the square root of the variance is sigma. Anyway, you can see that this is linear because you've got 1 on sigma multiplied by x minus this constant term. And so, practical real world sort of stuff here, the variance is the standard deviation squared, as I said. Hopefully I said that correctly. Anyway, if we were to think about this is sort of like a real world example, let's imagine we've got 2 people. We've got athlete A who does high jump and they clear 185 centimeters. We've got athlete B and they throw at 21 meters. If you think about those 2 sports, they have very different distributions and variances of ability, right? Because they're completely different sports. How are we going to compare high jump and shot put? Well, what we can do is we can apply this linear transformation to find out whose score is statistically more impressive or exceptional. And so if you do apply this transformation, and see if you can do that, see if you can apply this transformation. Have I given you enough information? Maybe not. But in any case, if you apply a transformation, you'll get a z-score. And that z-score for the high jumper is plus 2.4. So what that means is they're 2.4 standard deviations above the mean. And the shot put person is 2.1 standard deviations above the mean. So clearly the high jump person has a more statistically anomalous score. So they're more impressive or more exceptional. And so if we just plot those points on the graph, we can see that they're here. Over here. And so mathematically we say that athlete A is more elite because she is further into the tail of the curve. So this person here is further to the right of the curve. And as you can see, the further down to the right of the curve you go, the less and less people, the less and less likely you are to find people on that end of the distribution or that far into the distribution. So that's really hopefully giving you a solid foundation in linear combinations of continuous random variables. And yeah, I think the standard z-score is a really good example of a linear transformation. And again, the sort of key takeaway is that the variance is invariant to a horizontal shifts, but we saw from before that it does change. The variance changes as a squared when you apply that linear transformation to your continuous random variable. It becomes a squared. So we've got our new distribution here, 2x minus 140, and then so the variance changes as this a value, which is 2 squared. All right, hopefully that made some sense. Good luck with all your studies. Give us a thumbs up if you found it useful, and talk to you soon.